Hello, I will be presenting the paper Decision Theory Meets Explainable AI, which is really on the history, background, and concepts of contextual importance and utility. My name is Kary Framling, and I'm a professor in data science at Umeå University and the head of the Explainable AI team there. So in explainable AI, I believe we should really think about who the explanations are intended for. So once we have our great black box AI that is capable of taking good decisions and giving good recommendations, it's not enough just to produce hopefully detailed explanations and usable explanations for the domain experts, such as the doctor here, with very specific vocabulary and so on. I don't think most correct explainable AI methods actually can produce even this kind of explanations. It's just as important to be able to actually produce this kind of short and understandable explanations for end users, such as the patient here, so that people maintain trust in the reasoning and the recommendations of black box AI systems. It seems to me, though, when I read explainable AI papers in different places nowadays, it's not very often that I see examples of explanations of black box reasoning that could even potentially be understandable by this kind of end user. Now, coming to contextual importance and utility, the background and history is that when I started my PhD thesis work in 1991, there was an initial project for the PhD thesis, which consisted in selecting a waste disposal site for ultimate industrial waste in the region of Rhône-Alpes in France. So that was a real use case. There was over 3,000 potential sites to choose between. Now the local decision makers wanted to use classical multiple criteria decision making methods, but quickly realized that there were quite a lot of challenges with that kind of methods and specifying their parameters and so on. So the idea was, well, what if we could learn from past experience through machine learning instead, and use that? But in any case, it's necessary to explain the recommendations and decisions to citizens, inhabitants, and decision makers. And especially in this kind of a use case, the people concerned by the decision they needed some really convincing explanations. So we implemented several different decision support methods, such as rule-based reasoning, for which we could produce this kind of explanations, of course, in French. So what we're mainly showing is the rules which were used for coming to a certain conclusion about certain site. We also used the analytic hierarchy process, which is more or less a hierarchical weighted sum in practice. And here we are using concepts such as importance, important 9.5%, quite important 5%, and also classification of values, so very good value, bad value, and so on, which is what we call the utility, so importance and utility. The method that was used in the end is called Elector 1, which also used in this case weights and utilities, but it's based on parity, optimality, and pairwise comparisons between the different options. So anyways, how to explain machine learning based decisions? Well, we used neural nets for learning preference functions, and that, as we know now, leads to black box problems. We did speak about them already back in the 1990s. So the idea or the objective that I wanted to achieve was to try to explain black box reasoning in the same way as humans do when we produce retrospective explanations. For instance, on choosing a car, if I need to explain why I bought a specific car to my friends versus to my wife, I might be using different aspects, and I would start from the most relevant features first, presumably. But the point is that for different users in different situations, we might need different abstraction levels in our explanations, different vocabularies, and so on. And that's the reason why for choosing the word or the concept of context, and why the method is called Contextual Importance and Utility, or CIU. Now, if we have a look at these different models, so we have the linear models where we have weights and input values that correspond to utilities. So these are kind of the best explanations that we can produce to end users, the weights and input values. When we have classical rules or decision trees, that might give us this kind of decision function, which is non-linear, but it's also non-continuous, and it could be a challenge for many of the current explainable AI methods to deal with this kind of models. But then we come to the interesting part, which is nonlinear models. So here we have a very simple nonlinear model with 2 inputs and 1 output. In practice, neural networks and other models quickly get too many parameters for producing any kind of understandable outcome explanations if you start using the internals of the model for explaining to end users. One conclusion that I did come to also during my thesis, that using a local linear approximation around the point of interest or the interesting instance is not really valid, or doesn't produce the kind of explanations that are expected for this waste disposal, site selection, and similar tasks. So that took me to this contextual importance of utility and specifying them, which so if we in the weighted sum we speak about importance and utility or input values, contextual importance and utility is essentially a nonlinear extension of those concepts, and we have 3 ranges which are the main elements in calculating contextual importance utility. So we have the biggest possible range within which a certain output can change for classification tasks. This is typically 0 to 1. Then we have the range of output values that we can achieve by modifying the value of 1 or more inputs within reasonable limits. And this gives us or takes us to the definition of contextual importance, which is the ratio between this range and this range. Then the third range of interest is this one, the difference between the current output value and the minimal value observed when modifying the values. So contextual utility again is defined as the ratio between this range and this range here. Now, these definitions lead us to the following properties of CIU. It is completely model agnostic. It doesn't matter what kind of model decision support model you have, or what kind of black box you have. It can be neural nets, rule-based systems, decision trees, linear models, whatever. CIU doesn't create any kind of intermediate interpretable model. So that means that the explanations based on CIU actually correspond to the real reasoning of the black box by definition. It is also applicable to any abstraction level, meaning any combination of inputs, and we call those intermediate concepts here, which as a difference to input features and the actual outputs of the black box. To look further into detail, so this we have a look at the simple classification task of classifying iris flowers, which is also simple to understand. 3 possible classes and 4 input features. Now we have a flower which has these feature values: sepal length of 7, petal length of 6, and so on. And this flower is an iris virginica with a probability of 0.861 according to our neural network. Now, why is it an iris virginica? Well, we can see clearly that it's a petal length, which is obviously the by far most important input feature here, and we have very typical value for the petal length. And for the other features, they have less importance, but the values are still good enough. Then if we want to know why this is not an iris versicolor, the probability of that is 0.117. Well, we can see again that also for versicolor classification, the petal length is the most important feature, and we have very non-typical value for the petal length. If it would be even just a little bit smaller, then it might be a typical versicolor, but it is not in this case. The current R implementation of CIU can provide you with this kind of visualizations also, where the bar length of the bars corresponds to the importance of the input features, and the color corresponds to the contextual utility value. So a darker green is a very good value, and a dark red is a very bad value. So we can see here for Virginica that we have very typical values for Virginica, and the petal length is the most important one. For versicolor, we have the same thing, but the other way around. And for setosa, it's definitely not a setosa, no matter how we would modify the input values. We can also calculate intermediate or combined concepts in this way. So if we plot out the effect of sepal size and shape for the classification or the output of Virginica, you can see it here, and on the right side you can see that you can clearly see that the petal size and shape has a much greater influence on the classification or on the probability value of being a Virginica. Then the same thing for versicolor, where obviously we have very bad value for the petal size and shape, and that's the most relevant feature, the petal leaf actually. Then if we go to explanation vocabularies, we can have define a very simple vocabulary using what I just said, sepal size and shape, petal size and shape. And as we can see, this is the same explanation that we had before, but on a much higher abstraction level. All the results and figures shown in this paper and presentation can be found or produced by the open source, the source code published at this address, and you can also find generic R implementation of CIU at this address. We also have CIU implementations in Python and MATLAB that you can see here. A quick look at the CIU R package takes us, it looks like this. So you can find the same things as in this presentation here. You can also find the actual code that when you run that, you will get the output outputs and figures that you see here. And the models that we are using here, it's LDA and random forest for the iris task. Another example is the Boston housing dataset, which is a regression task, and we're using gradient boosting in this case for demonstrating how CIU works. And here you can see the same kind of plots that you saw already, but for the Boston housing task. So the ongoing and future work and challenges around CIU, we will focus quite a lot on comparisons with other explainable AI methods, notably regarding the end user understanding of the produced explanations, and that's very much related to the use of intermediate concepts and vocabularies and dialogues and so on. We do also have ongoing and submitting work on saliency maps, which is seems to be quite a hot topic in explainable AI in general. In general, we will be working more on more data sets and applications, and notably focus towards real-life applications such as fault diagnostics in machines, where it's quite crucial also to explain and understand why we think a machine is going to break down and in what way, and so on. Okay, thank you. I hope this presentation made you interested in CIU, and if so, please go and have a look at the GitHub sites. Thank you.